Hello and welcome to a supplementary video on the area of a circle. In the previous video we asserted that the area of a circle is pi r squared, but we didn't go into explaining why the area of a circle is pi r squared. Now this video is purely optional and it's for people who, like me, have difficulty remembering things that they don't believe. So I'm going to try and convince you that the area of a circle is indeed pi r squared. Now I think the first thing I want to do is let you in on a dirty little secret that maths teachers have been keeping from you, and that is concerning angles. Generally what you've been taught is that we can divide a circle up into 360 equal divisions, which we call degrees. And that's all well and good, but there is a better way to divide up an angle, or to show an angle. And what if we divide the circle into a proportion of its circumference? Now if I take the radius of a circle, this is actually a more intuitive way of showing an angle. If I take the radius of a circle, the distance from the centre to the outer edge, and if I take this same length, let's pick a colour, let's pick this colour, and if I can bend this radius around the outside of the circle, so it might look something like this, and then I can join it again with another radius. Now if this distance around the outside edge is the same distance as the two radiuses, so this is a radius, this is a radius, and this length here is also one radius, then the angle that subtends this length, the word subtend, it just means that joins, the angle between two lines that join either end of this arc is called 1 radian. And now we don't have to remember anything like, oh, there's 360 degrees in a circle. We can just say there are 2 pi radians in a circle. It's as simple as that. So this is actually a simpler way of dealing with angles that you will find at A level standard. So when you get to A levels, they actually say to you, actually don't bother with degrees anymore, we're actually going to teach radians as a measure of angles. But for the purpose of your GCSE exams, you must remember to use degrees. You won't abandon degrees unless you're planning to take your maths beyond the GCSE syllabus and into your A levels. And you won't get any extra points at GCSE level for using radians, so pretend you didn't hear this from me, and when you do hear about radians, if you do take A levels, just pretend that it's a surprise to you, that you've only just learned about it. Now when you're doing your exams, it's really important that you use your own calculator, that you are familiar with how it works. And when you get your trigonometry questions like sine, cosine and tangent, make sure that your calculator is set to the right settings. And for GCSE exams, the right setting will always be degrees. But now you've seen that your scientific calculator might have something like D, R and G, or it might say deg, rad and grad, or degrees, radians and gradians. But now you know what this radians or rad or R is all about. It's about measuring an angle as a proportion of the circumference of the circle, where the circumference of the circle is the length of one radius, and that is 1 radian. So instead of having 360 degrees in a circle, we have 2 pi radians in a full circle. Now what's the point of having radians, you ask? Well, it makes something really simple when we're dealing with very small angles. Now if I'm working in degrees and I want to find the sine of, say, 1 degree, and I look for the sine, well, note it actually says 0.017, so the sine of 1 degree is nothing like 1. But if I work in radians, the sine of 1 radian is 0.84, which is not too far away from 1. Now let's work closer. Let's take degrees and let's take, say, 1/4 of a degree and find the sine. We see that it's 0.004, which again is nothing like 1/4. But if we go into radians and we take the sine of 0.25, it's actually 0.247, which is very close to 0.25. In fact, if we divide that by 2 again and say 0.125, and we take the sine, that's actually 0.1246, which actually rounds up to 0.125. And if we take 0.01 and we find the sine of that, it's 0.0099998, which is really, really close to 0.01. This is called the small angle approximation, and it only works in radians. We can say that the sine of an angle is roughly equal to the angle, but only in radians and only if the angle is really, really small. The other thing to note is that as the angle gets really, really close to 0, so the cosine of the angle gets really, really close to 1. So if the angle is very, very small, the cosine of x, if x is small, will be very, very nearly 1. I'll try and give you a little bit of a glimpse as to what I'm talking about with some trigonometry here. So here's a right angled triangle. And we can remember from our GCSEs, which we are doing, that if this is the hypotenuse, this is the adjacent, and this is the opposite, then our angle would be here. Now the adjacent over the hypotenuse is the cosine, so it's the relationship between the adjacent side and the hypotenuse that gives us our cosine. Now for the cosine to be nearly 1, then h over a must be very nearly, or must be 1, which means that the hypotenuse must be equal to the adjacent. And for the hypotenuse to be equal to the adjacent, there can't be any angle between them. So as this angle gets smaller and smaller, so let me draw a really small angle. You can see now the hypotenuse is very nearly the same length as the adjacent. So the hypotenuse divided by the adjacent is almost 1, and the hypotenuse over the adjacent is the cosine. Okay, so with that covered, let's talk about circles. If I divide this circle up into radians, there's going to be just over 6 of them because There's 2 pi radians in a circle. I'm not even judging the angles very well. But we've got these circles like this. We've got these angles like this. If I join these to make triangles, you can see that there's an awful lot of gap left over. That's not going to be a very accurate representation of the area of the circle. However, if I split this into much smaller triangles, so if I have a tiny little triangle here and another tiny little triangle here, the amount of gap left over is very small. In fact, if I have ridiculously small number of triangles, like if I fit 1,000 of these triangles into one radian, I will have triangles that are so small that the gap left over is negligible. So if I have these triangles really small, my other advantage is that because of this angle here is small, then I can use these small angle approximations to make calculating the area of the triangle really easy. In fact, the area of the triangle is just a half of the base times the height. Now if I've got a right angled triangle, well if I've got a isosceles triangle where the 2 longer lengths are the radius, so this is R and this is R. Now if I draw a line in the middle to get the height, if the angle here is really small, then this height here might as well just still be R, because the cosine is very nearly 1. So we can say that the height of the triangle is just R. And because this angle is really small, we can actually say that the base, because these angles, if this is like 0.0001 or something, the internal angles have to add up to 180 degrees, so 0.00001 radians is going to be a negligibly small amount of degrees. So one of these angles could be considered as 90 degrees and the other one is as near as you like to 90 degrees, not quite 90 degrees but very close to 90 degrees. We can approximate this isosceles triangle. It can be a really close approximation to a right angled triangle, so we can say that this base here, using the small angle formula here, is pretty much whatever our angle is. I'm going to call it x. Instead of radians, it'll be radiuses, or x times a radius. Cannot write very well. So our formula, our area for our triangle becomes a half. Let's say arbitrarily that we've got 1,000 small triangles in one radian, so that's 1,000th of a radian angle, so the base is 1,000th of a radius, or 1,000th of r. So that's R divided by 1,000. So that's a half times R over 1,000 times the height of the triangle, which you said is as near as makes no difference to the radius. So that's the area of one of our really tiny triangles. Now we said we'd have 1,000 of those triangles in 1 radian, so we have to multiply by 1000 triangles to make 1 radian, and then we have to multiply by 2 pi radians to get a complete circle, because there are 2 pi radians in a circle. Okay, so our area of our circle is 1/2 times the radius divided by 1000 times r times 1000 times 2 times pi. Well, this 2 here can cancel out with this half, and this r over 1000, the divided by 1000, can cancel out with the times by 1000. If you've got r over 1000 and then you've got 1000 of them, you're going to end up with your r. So our area of a circle, what are we left with? We've got no half, we've got an r, we haven't got the divided by 1000, we've got another r, and the 1000 has gone and the 2's gone, and all we're left with here is the pi. So our area is r times pi, which is the same as pi times r, and anything multiplied by itself is squared. So that's pi times r squared, or pi r squared. Okay, I hope that wasn't too hard. Now I hope that you can understand why the area of a circle is pi r squared. You might find it a little bit easier to remember. But remember, for GCSEs you only need to know that the area is pi r squared, but hopefully now that it just makes more sense. Now, if you are doing your GCSEs this year, don't harass your maths teacher with questions about radians. Leave that if you want to do A levels. And if you do accidentally drop that you know about the existence of radians, you didn't hear it from me, okay? Alright, well, I'd like to wish you all the best with your revision and all the best with your exams, and I'll look forward to seeing you in the next video.